Okay, so whenever you're graphing a rational function, first thing you want to do is factor everything. So that's what I have done here. All right. First, we're going to look at the zeros of the numerator. So those are going to be 2 and 3, and also the zeros of the denominator, which is 1 and 3. All right. So those are common zeros, 3 in the numerator and denominator. So that's going to be a whole. And another thing I'm going to do here to just make this explanation a little easier, instead of calling this y, I'm going to call it f of x. Okay, so we'll come back to the whole in a second, but since 2 is only a degree of the numerator, we're going to put a 0 there. And since 1 is only a 0 of the denominator, that means there's going to be a vertical asymptote at 1, for reasons explained earlier in the videos. If we were to plug in 0 to find the y-intercept, then f of 0 ends up being 2. So you put a point right there. And since the degrees of the numerator and the denominator are the same, we could find the horizontal asymptote by dividing their leading coefficients. So I'm going to put a dotted line right here through y equals 1. Okay? Now, I'm just going to connect the dots. Now, sometimes this is easier said than done. In this case, since there's only one vertical asymptote, we don't have to really plug in many extra points. But before I get too ahead of myself, we actually have to find the whole. Let's do that too. So the whole is going to occur at the x-coordinate. That's the 0 of the numerator and the denominator, which is 3. Okay. Now, if we plug 3 into the numerator and the denominator, we get 1 over 2. So that means we're going to use this point 3, 1/2, but keep it as an open circle because it's not actually part of the graph, but it's going to kind of go through that point. So it's like it's undefined there, but we could still use that point to graph. Okay, now we're just going to connect the dots. So if we start on the left here, all right, there's a horizontal asymptote. It's going to get closer to there. It's going to go through this point, and then it has to go up. The reason why is because if it went down, it would have to cross the x-axis, and there's no x-intercept there for it to cross. Okay. Then on the other side, it's got to go through these 2 points. All right. I guess theoretically it could bounce up, but since x equals 2 is a 0 with a multiplicity of 1, it's not going to bounce. So instead, it's going to go through that point. All right. And it's also going to continue through this point and get closer and closer to the horizontal asymptote. All right. And that's what the graph would look like right there. The domain, though, would still be x can equal 1 or 3. Okay, now let's try this problem. First thing I'm going to do is factor this. If you want to try that on your own, just pause the video now, and I'm going to pause it too. Okay, and that's what we get, and I don't know where the accent came from, and I called it f of x. All right, so now let's plot. Why don't you try graphing the x-intercepts and the vertical asymptotes? Okay, so we would have an x-intercept at -9 and also at -2. And there'd be a vertical asymptote at -1/2. Okay, now find the y-intercept. Okay, so the y-intercept is going to be at 0, 18. Okay, now we need to look for a vertical asymptote, horizontal asymptote. But since the degree of the numerator is bigger than that of the denominator, there's not going to be one. So what we're going to do is find the slant asymptote by doing long division. So I'm going to do that if you want to try that on your own. And then pause the video and check it up. Okay, so when you get long division, it's a little messy, but you get something like this. 1/2 x plus 5.25 plus 13 over 2x plus 1. So this part is going to be irrelevant because when x gets really big, that's going to approach 0. So now I'm going to find y equals 5.25 on my y-intercept and use a slope of 1/2 and graph my slant asymptote. Now I know this is not drawn to scale, but if you either use slope or found the x-intercept of this line, you would see that it would have an x-intercept of 10.5, which puts it right around here. Okay, and now if we draw this dotted line, we can now connect the dots. Now again, it's a little messy, but we actually have enough information here to see that, well, if you plug in a point, let's say into the original equation, you plugged in something like -10 into here, you would see that this would be negative, but it would also get closer and closer to the slant asymptote. Alright, then it's going to have to go through this point, and it's going to get closer and closer to the vertical asymptote. Alright, it has to go through this y-intercept, and it's going to go up towards this vertical asymptote, because if it went down, there's no 0 for it to cross. And then, you know, it could bounce around here, it's not, but then it's going to get infinitely closer to this slant asymptote. If you're unsure about how any of this graph looks, you can always just plug in more points. You could also look at this graph in factored form, which I'll write right now, and use a sign chart to see what it looks like. So like if you plugged in something into here that was less than -9, you would see that it would be negative, so this whole part of the graph is going to be negative. And if you plug in something on this interval between -9 and -2, you would see it's positive, so you get the part above the x-axis. Alright, and then so on and so forth. You would also plug in a point on this interval in between the 0 and the vertical axis, vertical asymptote, and you see it's negative. Alright, and you plug in something to the right of -1/2, you would see that it's positive. Okay, just to finish up with some vocab that I may or may not have talked about in these videos. First is infinite discontinuities. Alright, that's just a cool word for vertical asymptotes. So anytime you see a vertical asymptote, you can also say, like in this case, that there's an infinite discontinuity at x equals 0. Because at x approaches 0, y is going to approach infinity. And it'd be the same thing if it was negative infinity. We'd still call that infinite discontinuity. Alright, so infinite discontinuity implies vertical asymptote. And removable discontinuities is another word for hole. So you just think about just removing one part of the graph would be, removing one part of the graph, like one point. Think of it that way. There's going to be a hole. So another word for removable discontinuity is hole.